When most people think about a space mission, they picture the launch. They picture the rocket, the countdown, the flames, the cameras shaking like the world itself has been startled awake. And fair enough, launch is the glamorous part. It is the bit that gets posters, montages, and swelling music. But the truth is that a space mission is not mainly a launch. A launch is one violent paragraph in a very long book. A real space mission begins much earlier, usually with a question. Someone wants to know something, do something, move something, watch something, map something, defend something, or prove something. That is the seed. Before there is a rocket, before there is hardware, before there is even a sketch on a whiteboard, there is a purpose. That purpose might be scientific. We want to study Mars. We want to measure solar radiation. We want to observe black holes, or track climate patterns, or understand how plants grow in microgravity. It might be commercial. We want to launch communication satellites. We want to provide internet coverage. We want to sell imagery of the Earth. It might be military. We want missile warning. We want secure communications. We want better intelligence. It might be political. We want prestige. We want to prove industrial strength. We want to show that our country can still do hard things without holding a committee hearing until the sun burns out. That first step matters because the purpose decides everything that follows. If your mission is to take pictures of hurricanes, you need one kind of spacecraft. If your mission is to land on the moon, you need another. If your mission is to put astronauts in orbit, you need a very different system. Because human beings are demanding passengers. Cargo, to its credit, rarely files complaints. Once the mission has a purpose, planners turn that purpose into requirements. This is where dreams put on a necktie. A mission cannot live on vibes. It needs specifics. How much mass are we sending? Where is it going? How long must it operate? What data must it collect? How often? With what precision? What are the temperature limits? What level of risk is acceptable? How much money is available? How soon does it need to fly? That last one is always fun because the answer is often very soon, spoken by someone who will not personally be soldering anything. From those requirements, engineers begin designing the mission architecture. That phrase sounds grand, and in a sense it is. Mission architecture means the overall shape of the endeavor. Will it use one spacecraft or several? Will the satellite operate in low Earth orbit, geostationary orbit, lunar orbit, or deep space? Will it communicate directly with Earth or through relays? Will it rely on solar panels, batteries, radioisotope power, fuel cells? Will it stay in space forever, come home, crash deliberately, or land gently if Providence smiles? This is where trade-offs begin. And trade-offs are the real engine of spaceflight. Everyone wants maximum performance, minimum cost, perfect reliability, fast delivery, low mass, long life, and no drama. They would also like a pony. The universe is not obliged to provide these things together, so mission teams start choosing. A bigger spacecraft can carry more instruments, but it costs more to launch. More redundancy may improve reliability, but it adds mass. A faster schedule may please leadership, but it often terrifies engineers for reasons that later become obvious to historians. Once the architecture starts taking shape, the spacecraft itself gets broken into subsystems. This is where the machine becomes less like a single object and more like a tiny flying city council, except with fewer speeches and slightly better discipline. There is the structure, the physical frame that holds everything together. There is propulsion, if the spacecraft needs to maneuver. There is power, usually solar panels and batteries, sometimes stranger arrangements for stranger missions. There is thermal control, which keeps components from freezing, frying, or suffering some more creative insult in between. There is guidance, navigation, and control, which helps the spacecraft know where it is pointed, and how to correct itself when space starts misbehaving. There is onboard computing, which manages tasks and responds to problems. And then there is the payload, the part that actually performs the mission, whether that means taking images, collecting signals, measuring particles, carrying cargo, or hosting human beings with all their heroic fragility. All these parts have to work together. More than that, they have to work together after being shaken like cutlery in a tavern brawl during launch, and then left alone in vacuum for months or years. That is a fussy design problem. So the mission enters the long middle phase, where concept turns into hardware, and paperwork multiplies like rabbits in a wheat field. Engineers build models, they run simulations, they analyze failure modes. They write software, they design electronics, they select materials, they talk to suppliers. They discover once again that suppliers are mortal and therefore capable of delay. At the same time, mission planners work on operations. This part gets less public affection than it deserves. People love rockets. They are less enchanted by shift schedules, communications windows, command procedures, and anomaly response playbooks. Yet missions live or die by operations. Someone has to decide how the spacecraft will be used once it is in space. When does it collect data? When does it transmit? What happens if a sensor fails? What happens if power drops? What happens if the spacecraft goes silent? What if it starts tumbling? What if it survives perfectly, but sends back gibberish like a possessed typewriter? You do not want to invent those answers while the mission is already in trouble. So teams rehearse. They create procedures. They run tests. They assign roles. Some people handle flight dynamics. Some monitor health and status. Some control the payload. Some coordinate ground stations. Some analyze incoming data. Space missions may look solitary from the outside, one little object gliding through silence, but on the ground they are often crowded human enterprises. A satellite can have the emotional atmosphere of a small kingdom. Everyone depends on everyone else, and someone is always worried about a chart. Then comes integration and test, one of the least glamorous and most important phases in the whole process. The spacecraft parts that were designed separately now have to be brought together into one working system. This is where elegant drawings meet physical reality and discover that physical reality has opinions. Connectors do not fit. Software talks past hardware. Components interfere with each other. Thermal assumptions turn out to be optimistic. Vibrations reveal weaknesses. A mechanism jams. A sensor drifts. Power margins shrink. A cable turns out to be routed in a way that makes an otherwise intelligent person stare into the middle distance for several minutes. This is normal. Disturbing, yes, but normal. That is why missions go through so much testing. They are tested electrically, mechanically, thermally, and functionally. They are placed in vacuum chambers to mimic the conditions of space. They are shaken to simulate launch. They are heated and cooled through expected extremes. Their software is run again and again. Their operational timelines are rehearsed. Their failure cases are probed. You want the spacecraft to reveal its bad habits on Earth, where people with tools can still insult it properly. Meanwhile, launch arrangements are moving forward. A spacecraft does not launch itself, no matter how high its self-esteem. It needs a rocket, a launch site, a schedule, and a fair amount of coordination. The spacecraft is typically delivered to the launch site and processed there. It is checked again. Then it is integrated with the launch vehicle, often inside a payload fairing. For a little while, this priceless machine sits inside another priceless machine, and everyone behaves with the solemnity of men carrying a wedding cake across a frozen pond. The launch vehicle itself has been through its own production, inspection, and preparation cycle. Its stages are assembled, its engines are checked, its software is loaded, its fueling systems are prepared. The range is coordinated. Weather is watched with the kind of bitterness once reserved for medieval plagues. Wind, lightning, upper atmosphere conditions, ground equipment readiness, boats in the wrong area, any of these can delay a launch. People sometimes treat scrubs as failure. In truth, scrubs are often signs that adults are still in charge. Then, at last, comes launch day. The countdown is not ceremonial fluff. It is a structured sequence of technical steps. Systems are powered up. Communications are verified. Tanks are loaded with propellant, sometimes chilled to extreme temperatures. Final go or no-go polls are taken. Then the engines ignite. At that point, the mission enters its most violent minutes. The rocket lifts off, climbs through the lower atmosphere, throttles as needed, sheds stages as fuel is spent, and eventually places the payload on the intended path. The fairing usually separates once the dense atmosphere is left behind. This is the moment the spacecraft first sees space directly, which is moving if you are a poet. and terrifying if you are responsible for the thermal coatings. If all goes well, the spacecraft separates from the rocket. That is the end of launch and the beginning of actual mission life. And here's the part many people miss. Separation is not victory. Separation is merely survival with potential. The spacecraft now has to wake up properly. It has to orient itself. It may need to deploy solar panels or antennas. It must establish communications with the ground. Telemetry starts coming down, and the mission team studies it like priests reading omens, except with better math. Is power stable? Are temperatures acceptable? Did deployment occur? Is the computer healthy? Is the attitude under control? Is the payload alive? This early period is called commissioning, and it is one of the most anxious times in any mission. The spacecraft is in space, which is wonderful, but it is also in space, which is terrible. Things can still go badly wrong. A panel may fail to deploy. A valve may stick. A software issue may appear. Everyone is relieved, but nobody is relaxed. During commissioning, the team gradually tests the spacecraft systems and proves that it can perform the mission it was built for. Instruments are powered on. Calibration begins. Data products are checked. Only after this phase is complete does the mission enter routine operations. Routine operations sound sleepy, but is often the long productive heart of the whole enterprise. In routine operations, the spacecraft does what it was sent to do. A weather satellite watches storm systems. A communication satellite relays signals. A scientific probe measures particles, fields, or planetary surfaces. A navigation satellite sends timing signals. An imaging satellite photographs the Earth. A telescope stares into distant darkness and returns whispers from the far side of time. On the ground, operators monitor health, execute commands, plan activities, and respond to problems. Data flows into processing pipelines, then to scientists, analysts, customers, or military users. This is where the mission produces value. Without this phase, the launch is a very expensive fireworks display with documentation. Routine operations can last days, months, years, sometimes decades. And during that time, the mission is constantly managed. Batteries age, fuel is consumed, sensors degrade. Solar storms may disrupt communications. Tiny faults appear. Ground teams troubleshoot, adapt, and keep the machine alive as long as they can. This is why space missions are often described as flying laboratories or flying systems rather than static objects. They are not launched and forgotten. They are lived with. They are tended. They are coaxed along. They are sometimes persuaded to outlast their designers' expectations through a mix of engineering discipline and what can only be called dignified improvisation. Crewed missions add another layer entirely. If astronauts are involved, then the mission includes training, medical support, life support systems, habitation systems, emergency planning, re-entry planning, and 1,000 little details that exist because the human body, for all its majesty, was not designed for orbit. Astronauts train for years because space is full of ways to die from something embarrassing. A loose checklist item, a failed seal, a misread cue, a wrong switch setting. People romanticize courage, and fair enough, but missions work because courage is paired with ritual, discipline, and repetition. For missions that leave Earth orbit, things get even more elaborate. A mission to the Moon or Mars or beyond often includes cruise phases, trajectory correction maneuvers, gravity assists, entry systems, landing systems, surface operations, and longer communication delays. Once you get far enough from Earth, the ground cannot micromanage in real time. The spacecraft or lander needs more autonomy. It must make some decisions on its own, or at least respond quickly to conditions before Earth can advise it several minutes later. That changes software, operations, risk, and design philosophy. Then there is the end of the mission, which deserves more respect than it usually gets. A space mission is not complete when the good data comes in. It is complete when the system is shut down, disposed of, or retired responsibly. For some satellites, end of mission means deorbiting, so they burn up in the atmosphere. For others, especially those in geostationary orbit, it may mean moving to a graveyard orbit, so they do not clutter valuable operational lanes. For probes and rovers, it may mean they simply stop responding, their little electronic lives spent in service. For crewed missions, it means re-entry, landing, recovery, medical checks, and an ocean of post-flight analysis. That post-flight analysis matters too. Space missions teach lessons, often expensive ones. Teams study what worked, what failed, what nearly failed, what design choices proved wise, and which ones seemed wise until they met reality in a dark alley. These lessons shape future missions. Spaceflight, like civilization itself, advances through accumulated correction. So when you stand back and ask how space missions work, the real answer is that they work as chains of disciplined decisions. A mission begins with purpose. That purpose becomes requirements. Those requirements drive design. That design becomes hardware, software, operations plans, and tests. Those elements come together for launch. Launch places the mission in space. Commissioning proves it can function. Operations produce the actual value, and end of life closes the loop. That is the hidden spine of the whole enterprise. People often speak of space missions as triumphs of technology, and of course they are, but more deeply, they are triumphs of coordination. Hundreds, sometimes thousands of people all have to pull in the same direction. A mission is a machine, yes. It is also an agreement. It is a temporary alliance between ambition and discipline. That is why failed missions are often so painful. They do not merely represent broken hardware. They represent years of organized human effort brought to grief by one flaw, one oversight, one unlucky event, one bit of physics refusing to negotiate. Space can be majestic. It can also be the stern schoolmaster of overconfidence. Yet missions keep flying. They keep flying because the rewards are real. Space missions expand knowledge. They provide services modern societies depend on every day. They reveal the Earth to itself. They show us other worlds. They tell us where we are, what surrounds us, and sometimes what we may become. And there is something else. A working space mission is one of the cleanest expressions of applied human seriousness you will ever see. No speeches can save a bad spacecraft. No branding exercise can charm a broken trajectory. In space, reality is hard, exacting, and faintly rude. That is part of its greatness. So the next time you see a launch, remember what you are really looking at. You are seeing the loudest moment in a long chain of thought. You are seeing years of design turned into fire. You are seeing an argument with gravity. And if all goes well, you are seeing the beginning of a machine's long, careful work in the dark.